Okay, so here's the graph we were looking at. And this was a graph of, we talk about variables vary. So on the x-axis, we have the variable of months since the first observation. And then the y-axis is the variable of rate of change, insects per month. So what does this point mean right here? What does this point mean right here? Because what this blue curve is just a set of a lot of points. So to understand what that blue curve is means that you understand what each point means. So how about this particular point? What does it represent or mean? Yeah.
30 insects per month.
30 insects per month. Is that all?
At 0.4 months.
At 0.4 months, right? So at 0.4 months after the first observation, the rate of change is 30 insects per month. So what's happening to the population at that moment? What's happening to the population? It's going down? It's going up. Because the rate is a positive 30 insects per month. The number of insects is increasing. So what did we say? We said at 0.4, the meaning of this point is at 0.4 months, the rate of change of insects is, the rate of change of the number of insects is 30 insects per month. So in the first month, when is the insect population the greatest? At around 0.2 months? No. It's in this. See, the rate of change is always positive in that whole in the whole time. The insects are always increasing. The rate decreases for a time span there. The rate's going down. It's slowing down, but it's still growth, right? So that the most number of insects that you have is at 1 month in that first month, because you've increased the whole time. Okay. So then it said, consider a constant rate at 25, consider a constant rate at 45, and consider a constant rate at 60. And you calculated a certain number of insects after 0.2 months at those constant rates. If we were talking about estimating the actual rate of change here, which one of those three might be a decent way to estimate what's happening in the first 0.2 months? The middle one, right? So this one, it's the rate down here. It's always too low. It's always less than all these. This one up here is always greater. This one seems like it's kind of in the middle. It's like kind of like an average of all the rates starting at 30 up to about 60. So maybe that 45, a constant rate of 45 insects per month would be a reasonable way to estimate the rate of change in the first 0.2 months. Do you see that? Okay, and then in the next 0.2 months, so now getting to the last question on the homework, in the next 0.2 months, so it seems like to me, 45 again would be a reasonable estimate for what's happening in those next 0.2 months. It starts higher than that, and then it's lower than that. And then the next 0.2 months, I estimated something like 22. Okay, about 22 would be kind of in the middle of the changing rate in that time frame. Okay, and then something like 16, and then something like 24. So I didn't specify that you had to use intervals of 0.2. If you use a different size interval, then that's okay. So, but I just followed along from that previous question that looked at the first 0.2 months, and I just made these 5 intervals of 0.2 months, doing my best to recreate the given rate function with constant rates. This is a key. So that's a simulated rate function of constant rates. Okay. What is it not? So look, no vertical lines, no rectangles. Why not? Because what I just said, it's not about areas. This is about insects. This is about insects, how fast the insect population is growing and how many insects we have. What does that have to do with area? It doesn't have anything to do with area. We're talking about how the insect population is growing and how many insects we have. So what we're doing is we're not forming rectangles. We are trying to recreate the rate function with constant rates. So there's no vertical lines, no rectangles. Okay? We're trying to do our best to mimic this rate function with constant rates. Why? Because the constant rates give us math that we can do math, right? We can actually calculate some number of insects. So what did we say here? So this was our K1. We said this was 25. 45, thank you. Try again. And I said this was 22. And this was 16 and 24. So you may have different numbers. You may have different interval widths. I didn't specify those things. But this would be one way to recreate the rate function with constant rates for the first month. Okay? And so how do we then find how many, to start with 105, was that it?
Yeah.
So the total number of insects? Would be, we started with 105, and then how would we calculate how many we gained in the first 0.2 months?
Add it to your rate times time.
That's right. So 45 insects per month for 0.2 months means this many insects were added on. We can't do that really easy calculation if the rate is continually changing. The rate is constantly changing or continually changing the way the blue curve is. We can't do this really quick and easy calculation to get a number of insects. That's why we reproduce it with the constant rates. Okay, so then again, same thing. And then I'll just go right to the last one, which was 24 times 0.02. Okay. And so what are we doing here? We got the initial amount plus K1 times 0.02. Or actually, what's our interval width? Interval width. Okay, so for the interval width that we use, we're going to use delta x. So dx, we said, was a variable, a changing amount of change. But delta x is like a fix. It's like that fixed amount of change that we're going to decide. In this case, our delta x is 0.2. So then K2 times delta x. All the way up to, how many were there? K5. So our initial amount plus a little amount of change for the first 0.2 months, plus a little amount of change for the next 0.2 months, etc. to the last 0.2 months. But notice that it's the same calculation over and over again. They're all K delta X. They're all K delta X. So we have a notation that we can just represent that without having to write it over and over and over again. So how can we write that instead? We have this thing called summation notation. So this capital sigma means sum up a bunch of things that all look like this. All of them look like K delta X. It's just that those K's change. So we can say K sub I. I is first going to be 1. And in this case, we're going to go to 5. So this is short. It's just a way of making compact notation for we're going to add the same thing together over and over again. Every one of those things is a K delta X. So it's going to be K1 delta X plus K2 delta X plus K3 delta X, etc. It's not a great K. Let's try that K again. Okay. All right, so this is called summation notation. It means add up that thing, k delta x, say, starting with I equals 1, ending with I equals 5. And then you get something like, what? Anyone? So what do we get for an answer approximately? 125 or something? Anybody remember? 136? Everyone's going to get something different, but you should be in this ballpark. Should be in this ballpark. Is that, a lot of people got something around 136, 137? I see some nods. Okay, good. Questions so far? So there's all this background, there's all this backdrop to where our goal is to understand integral, and understand the integral expression, and more specifically, or beyond that, understand the fundamental theorem of calculus. There's a lot of setup. There's actually, we're going to talk about, there's like 7 principles. That's what this journey that we're on of understanding the fundamental theorem, or understanding what an integral is about. And we haven't even gotten to the integral sign yet, okay? But we got to understand where it comes from. Okay, another way to, is there a question? Anybody got a question? Another way to simulate the changing rate function with constant rates. So here we're just kind of like eyeballing. We're saying what constant rate would kind of be in the middle of all the rates as they change. Let's do our best to estimate. But there's another way to do this, and that's to let the constant rate be the same as the actual rate of change at the starting value of the interval. So in that first interval of 0.2 months, what's the starting rate of change? 30, right? So in that whole first interval, we're going to let the rate of change be 30. Okay? What at 0.2, so at 0.2, what's the starting value of the rate in that interval from 0.2 to 0.4? Yeah, 57.5, 58, something like that. Something like that. Okay, what about from 0.4 to 0.6? Yep, looks like about 30. And then from 0.6 to 0.8. Yeah, like 14, around 13 or 14, okay? And then from 0.8 to 0.1, like 18, okay? Or 17 or 18. So this is, taking each interval, getting the actual rate of change at the left side of the starting value of the interval, and then letting that be the constant rate for the whole interval. This is another way to simulate what the rate of change function is. And then again, to get the total change in insect population, so I'm not including the 105, I just want the total change now. We would sum up, so this is our K1, K2, again, it's going to be I equals 1 to 5, K sub I. What does that mean? Sum up K delta X plus K delta X plus K delta X plus K delta X. It's just now we're systematically, instead of trying to eyeball something, we take the exact rate at the starting value of the interval, or the left side of the interval, let that be the constant rate for that interval. Okay, so this is called a left side approach to simulating the actual rate function. So left side approach. Notice, if you're thinking of these like flags, the flags fly to the right. Okay? So don't let that confuse you. Left side approach means taking the actual rate at the left side, or the starting value of the interval, to be the constant rate for that interval. And why do we do this? Because the math is easy. K delta x, we can get an amount of change if we have a constant rate. The math is easy. But what's the trade-off? What about the result that we get for the total change in population when we do it this way? It's not accurate, right? It's not accurate. Because that new black rate function is not the blue rate function. It's different, right? It's trying to be like it, but it's different. Okay, questions on that? So we have this problem of accuracy. Let's talk about that.
Excuse me?
Yeah.
Is it important to you that you stay at the same amount of intervals, like 0.2, 0.2? Or could you do like just the high point to there and then like the high point to low point there, making the...
So change the interval width?
Yeah.
You could. You can change the interval width, but usually for this calculus we don't usually. We usually pick an interval width at delta x and we keep it the same.
So that's gonna be
It wouldn't be incorrect to do it that way. Yeah. So when you get into more advanced calculus, the partition can have different. You can have different widths of intervals. All right, that's something that you explore later. But for our purposes, we just usually keep it the same. Yeah. Other questions? Okay, so let's look at our rate function here. Remember, variables vary. So what's our x-axis? X-axis is time going by. And as time goes by, the rate function, this is our flag, right? This was our lowering the American flag. For the most part, it was coming down at 0.75 meters per second, but there was this in between each pull of the hand, there's this, the flag kind of comes to a pause. So that's why the rate function is what it is there. Okay, so let's talk about. So now we're simulating that changing rate function with constant rates using the left side approach here. So now the function that's being swept out is this approximating function. This approximating function using the left side approach. So if I turn off the original function, how is this doing at simulating the actual rate function? How is it doing at simulating? Right now, I've got delta x at 0.3, the interval width at 0.3. How's it doing? Does it simulate the actual rate function well? Yeah, if you just saw this, if you just saw that, you would say, okay, most of the time it's going down at 0.75 meters per second, but then there's something else going on we can't really tell. So how can we get a more accurate simulated rate of change function with these constant rates? I think all of you know the answer to this. More intervals. More smaller intervals will then result in a better simulated rate function. So let's do it. So here is 0.1716. Delta x is 0.1716. Slightly better, but it's until we get to something like this where the actual rate function that we know starts to emerge here. So we know that's our actual rate function. Now it's starting, Now we're starting to get intervals small enough where we can kind of see what's happening. 0.0876. So even smaller. Here's intervals of 0.0227 seconds. Now this blue function is made up of all constant rates. They're just in really small intervals. But in each interval, you've got a constant rate. So it's possible to calculate amounts of change in the height of the flag for each little constant rate. So here's 0.005. If you're sitting in the back, you probably can't tell the difference between that and the actual rate function. That's not what I wanted. Okay, so what we want is being able to calculate exact amounts of change, not approximate amounts of change. What's the key to that? Making the intervals very small. And there comes a point when the intervals get small enough that there's no distinction between the actual rate function and the approximate rate function because the intervals are so small. And then our amounts of change then are indistinguishable as approximates or exact. Okay? So what do we need? We need these intervals to be small enough. Small enough. And when they're small enough, then what's actual and what's approximate, we can't tell the difference. They're essentially the same. Okay, so let's summarize the first. Now we've talked about lots of principles here, and let's summarize the principles here. Okay, what are we doing? We're making sense of this expression. This is our fundamental theorem expression. We're making sense of this. And now we kind of see what it's about. What it's about is it's for calculating some amount or an amount of change, like what you did with the insects, right? The goal was how much did the insect population change, or what was the total number of insects after a certain amount of time? So that's what this is about. Principle 1 was our constant rate of change. Constant rate of change. So let's review that. So what does 60 miles per hour mean? What does 60 miles per hour mean? That value of that quantity, 60 miles per hour. What does it mean? Get a partner and take a minute and just tell each other what you think 60 miles per hour means. Go.
Sorry.
Okay, so how many of you, the gist of what you said was every hour you go 60 miles. The gist of what you said, every hour you go 60 miles. Okay, that's a very narrow view of this. Okay, that's a narrow view of what this means. What's a full, broad view? What's a better view? That for any change in time, dx, what about your change in distance? What is your change? So 60 miles per hour tells you something about for any change in time, not just for 1 hour. Remember in the insects, we looked at changes in times of 0.2 hours. Okay? So for any change in time dx, what do we know? How far you went in that change in time. That the change in distance is always 60 times that change in time. So 60 miles per hour, it means you know how far you go in a half an hour. How far do you go in a half an hour? 30 miles. It means you know how far you go in 2 hours. How far do you go in 2 hours? 120. It means you know how far you go in 10 miles. 600. It means a lot more than just you go 60 miles in 1 hour. It means you go, for any amount of time, you go 60 times that amount of time in distance. Okay? So that's the way we want to conceive of constant rate of change. It's all wrapped up in this relationship, dy equals k dx. Okay? dy equals k dx. Second principle, changing rate of change. Changing rate of change. We said that lots, if not most, situations don't have constant rate of change. They have changing rates. So we looked at the flag example. Realistic rates are usually changing rates. And so we saw this flag. We said, the flag's coming down at 0.75 meters per second. But more realistically, it's pausing in between hand pulling, right? Principle 3, because we can't do mathematics with a changing rate, we're going to make up a pretend rate function, or a simulated rate function, made up of what? Constant rates of change. We're going to mimic the rate function with constant rates so that we can apply principle 1. Easy math, right? K dx, or k delta x. And then we're going to add up the changes to estimate the total amount of change. And we said that we can represent that adding up the changes as with the summation notation. Summation notation. Summing up a bunch of k delta x's to get the total amount of change. So a pretend rate function. Right? Here's using left endpoints. Something like this, right? Something like this. Okay, so that's the first 3 principles. Yeah.
The number above it, like if it said 5, that means that you're going to end at interval 5, or there's 5 intervals.
It's 5 terms that you're adding together.
Okay.
So that's the number of things that get added.
2, you would go to 6, even though it says 5. Because you need 5.
We can talk about this. It's not, for our purposes right now, it's not a crucial detail. So if you want to talk about it after class, we can hammer that out. But the important thing is that the sigma means sum up a bunch of things that are all the same. That's the general idea here. But we can have that conversation another time. All right. Principle 4. Make more smaller intervals. Why? What happens when you make more smaller intervals and recreate the simulated rate function? Right? Better pretend rate function, you get a better estimate of the change, or better estimate of the total amount. Right? Better ingredients, better pizza. Papa John's, thank you. Only the TA knew it. All right. So, okay, so yeah, that may be a matter of opinion, but this is not a matter of opinion. Okay? A better pretend rate function will give you a better estimate of the change, or a better estimate of the total amount. So here I'm showing a much smaller interval. With a smaller interval, you can see that's pretty accurate to what we know is the real rate function. So how do we? So we get a better estimate. We want it exact though. How do we get the exact change or the exact total amount? What do we do to the intervals then? Super small, right? Super small intervals. They just make them small enough. Once you get small enough, then you can't distinguish between the approximate and the exact. So as long as we're small enough and we can't distinguish, we've got it. Okay, so here's when the intervals get super small. What is our representation for the sum of all these changes k delta x? We're summing up a bunch of changes k delta x. So now with super small intervals, we have new notation for this. What is it? Does anybody know? When the intervals are super small, sigma becomes things they never told you. Integral, okay? So this capital sigma now for super small intervals is German S. The integral sign is German S, S for sum. So the integral sign is really an S for sum. What? Sum up a bunch of super small changes that we get the same way. Look, okay, what's our rate? Well, this is our rate function. It's kind of like all of the rates, one at a time. All the rates, one at a time, as they change, each one times a really small change in x. So this notation is completely analogous. Greek sigma, German s. Both mean sum. Before we have a bunch of constant rates k, well now the interval is so small that it's just virtually all the k's as constant rates are that continuous changing rate function. Right? So this is the rate function. But it's analogous to what we were doing with constant rates. It's the rate. And then we have our interval width now is dx. Very small interval width. Very small interval width. Summing up a bunch of changes. Each change calculated by rate times change in x. That's what both of those things say. It's just the one on the right is for very small enough intervals that it's indistinguishable from the exact rate and the exact total change. Okay, so there's two more principles. So we kind of got like the left side up there. So we understand what the left side now of the fundamental theorem is. So let's go back to our picture here. Okay, so now we've got this rate function. And we want to take a look at what about the height function? So can we imagine, visualize, sketch what the height function would be like for this rate function? Now I'll tell you that, let's say that I think the flag starts at 5 meters up, okay? So the flag is going to start at 5 meters up. The flag starts at 5 meters up, and the rate of change of height is according to this. Can you imagine can you sketch what that height function would be based on this rate function? So it's like the rate on the left and amount or magnitude on the right. In this case, the magnitude is height. Okay, so take a minute, see if you can sketch it, compare with the person next to you. So still seconds here. Okay. Did you imagine or come up with something like, so where's it at 0, where's it going to be? 5. And in general, what's this function going to look like? Starting from 5, what's it going to do? The height is going to decrease, all right? But then there's more subtlety here to it. It's not going to decrease at constantly, right? Instead, what are you going to have? Yeah, little places where it pauses, where it'll flatten out for a moment. So is this what you came up with? Okay, so now we have the rate. So our independent variable here is seconds, time in seconds. That's both x-axis. On the left, we're showing the rate, and on the right, we're showing the resulting height of the flag if it descends according to that rate profile or that rate function. All right, so now I have a question. In 2 different ways, represent the change in height of the flag from 0.7 to 1.8 seconds. So one way is going to relate to the graph on the left. Another way is going to relate to the graph on the right. Okay, so let's call this function, we're going to call this r for rate over here. So we'll call this one, say, r of x, where x is seconds. And let's call this one h of x for height. So this is the height function h. Values of the dependent variable h of x. This function here is r. Values of the dependent variable r of x. So we're going to look at from 0.7 to 1.8. There's some change in height of the flag over that interval. And same thing here, 0.7 to 1.8. So using the rate function, represent the change in height of the flag from 0.7 seconds to 1.8 seconds. Okay? An exact change of height. Okay? So we have to use what we've talked about so far in class. And then also using the h function, represent the change in height of the flag from 0.7 seconds to 1.8 seconds. Take a couple minutes. Go. An expression using the rate function that will calculate the change in height. And then an expression using the height function. Can we do it? Can you do it? So I'm talking about for small enough intervals, so you're indistinguishable from exact rate of change or exact change in height. Okay? Super small intervals. That's your clue. Super small intervals. Using the rate function, how would you express that change in height? Yeah. How would you express that change in height? Calculating, expressing. What symbols would you write? Would you write in the box so that what you wrote in the box represented the change in height? There you go.
changes throughout the period. So you have times the rate by the amount of time.
Good. Now what about that side?
Because it's like units per second.
No, an expression. No calculations, no numbers. We have an essentially changing rate function. How can we express the change in height using that changing rate function? What kind of expression? Principle 6. Principle 6 allows us to write a change in the quantity if you have a changing rate function. And what was that? Somebody save us. Integral, right? Integral. Summing up, starting at 0.7 and ending at 1.8. What are we summing up? A bunch of k delta x's. But the intervals are so small that that's essentially the rate function dx. That's what does it. Summing up, S, summing up a bunch of k delta x's, but the intervals are super small. So those k's are the continuous, each k put together then is the continuous rate function times the super small interval. Again, this is analogous to summation k delta x. That's what essentially that's what that is for super small intervals. All right, what about using the h function? What's the change in height? Final value of the height. We know h of 1.8 is the height at 1.8 seconds minus the initial value of the height. So if these are both expressing the change in height from 0.7 to 1.8, what can we conclude? They're equal. Last question. And then a summary. Last question. How are the functions h and r related? How are the functions h and r related? R is what relative to h? Rate of change, or the derivative. Right? If r is the rate of change of h, then r is the derivative of h. And therefore, h is the antiderivative of r, right? So if that rate is r, it's the rate of change or the derivative of h. Therefore, h is the antiderivative of r. These are the last two principles, and now we've got it. This is what the fundamental theorem is about. It's about calculating a change in a quantity. You can express it using the rate with an integral. You can express it with the quantity function as final minus initial. Final value of the quantity minus the initial value of the quantity. So let's summarize. Ready? Principle 6. Two ways to represent an amount of change. We can use the rate change function and integral, and we can use a quantity function, final minus initial. So the left side up there is the first. And the right side up there is using the quantity function, final value of the quantity minus initial value of the quantity. Calculates the total change. Principle 7. The quantity function f is the antiderivative of the rate of change function little f. So if we actually want to calculate that amount, what do you prefer? Partitioning up the thing and adding up a bunch of little changes, or doing f capital F of b minus capital F of a? What do you prefer? What's easier? The right side. So we're going to, in general, we're given, or we set up expressions using the rate, and then we calculate those expressions using the right side, using the actual amount function. Why? By getting the antiderivative of the rate function, and then plugging in the final value, plugging in the initial value and subtracting. So in general, we're using the right side to compute or calculate expressions from the left side. Okay, so there's the written homework posted.